Now, to use this, let's take a simple example. Let's say we have an image of resolution 28x28, and this is a grayscale image. Now, what we can do is we can convert it to a vector. So in total, we'll have like 784 different elements or 784 different pixels. And let's say that's our input vector. So it will have like this dimension, and this represents X, which means that this is pixel level representation, which we were discussing earlier. All right. So your input vector X now has 784 different values. Now, in your neuron, then you need like weight for each of this input signal, right? So if you represent that neuron as W, which again will be a vector of weights, then it should have 784 different weights. And again, you can represent that as a matrix, or you can say like a single vector, right? And B is like a bias. So biases, usually you will have one bias for each perceptron. Okay. Now, what you can do is, as we saw in the previous slide, you just take dot product of X and W and add the bias. Okay. And if you do the math here for the shape of like this operation, this is the dimension of X, this is the dimension of Y. So this is going to give you just one number, right? That will be 1 cross 1, and we just add the bias. So essentially, you can represent this perceptron using this simple equation. And this is kind of parametric because X could be like of any dimension, and depending upon that, you will have dimension set for W. Okay, so this simple equation tells you how a simple perceptron will work. So of course, that was like, let's say a binary classifier, which was saying whether object is present or not. What if you have a set of classes, right? You can have 3 different classes. Now, what you can do is for each class, you can add a neuron. Okay, so let's say this is your input vector. You have 3 different values here. And for each class, you have this perceptron now. And each perceptron will tell you whether that class is present or not. So then you can solve like your multi-class classification problem. The operations won't change. But the only thing is for each perceptron, you will have that many parameters, right? All the arrows coming in. Because for each perceptron, you're going to take linear combination of your inputs. And for each neuron perceptron over here, you will have different set of weights. So those weights are not shared here. Okay, so let's try to understand how that will change the mathematical formulation. Your input vector is not going to change. It will still be 1 cross 784. Your weight matrix will change. Earlier, you had just one perceptron. So you needed like just 784 different values. But let's say you are solving a 10 class classification problem, which means you have 10 different object categories. For that, you will need 10 different perceptrons. So which means the number of parameters you need is 784 times 10. Okay, so 1 for each perceptron. So again, you can represent that as a matrix. And if you will try to follow, again, for each perceptron, you will have a bias. So in this case, you have 10 perceptrons that will give you 10 different biases. So bias, again, you can represent as a vector 1 cross 10. And your equation will not change. It will still be X times W plus B. In this case, your W is not like a vector, it's a matrix. But again, if you do the math and if you remember like how we did matrix multiplication, this is again going to give you 10 different numbers. All right. So at the end, you will get 10 values, and each value will represent one class. So in this case, one thing which is important is this is not your network parameter. This is input. These are your network parameters. Okay, so these W matrices, which are storing weights, which are actually which you are using to compute the linear combination. Those are the parameters which are actually learned when you train your model. We can simplify it further. So here it's a little, not complicated, but just from like computation convenience. Let's say we don't want to perform any addition. So what we can do is, and it's just a hack, you don't have to do this. So what you can do is you can move the bias inside your weights, right? And then you can add one more input and you can hard code that as 1. Now what will happen is if this B is the bias, it will be multiplied by 1, right? So it will still be B, but now you can represent that as a parameter in your network, which is your weight. And then your operation is simplified. You don't need any summation because you don't have like B outside of your matrix multiplication. Now that was like just clubbing different perceptrons together. But of course, what you can do is you can perform composition of these different set of perceptrons. And each set is called a layer. In this case, let's say you have this as input, and this is your input layer. You have 3 perceptrons here. And what you can do is whatever output you get from these perceptrons, you can add one more layer of these perceptrons. In this case, you have 4. And then you can have like your final output layer, which is just 1 neuron, which means you're just trying to solve binary classification. Okay, so you can make like these networks deeper and deeper. And the idea is like you want to represent complex functions using composition of smaller functions. Okay, again, to note that these are your input. Weights are actually these arrows, which are going from, which are transforming your input layer by layer. And the number of weights you have will depend upon these neurons. Okay, so in this simple network, if you have to count the number of parameters, then you just count these edges, because those are the weights of your network. So in this case, this is layer 1, this is layer 2, this is layer 3, which is again the output layer as well. Okay, this is sometimes called hidden layer. Again, this is hidden layer 2. You can also call this input layer. Then your final layer, this is also called output layer. And essentially all of these operations, as we discussed earlier, it's just matrix multiplication, which makes it very efficient. And we use like GPUs to train these models. And GPUs, like we have very, very efficient matrix multiplication operations. And that's why training these models is easier in GPUs. Okay, and these matrices are actually the weights of your network, as I said earlier.